Please welcome Vice President and Distinguished Engineer of Amazon EC2 Networking at AWS, Cole McCarthy.
Good afternoon, and welcome to the AWS Network Innovation Session. I started my career as a junior network engineer, making and labeling cables on the data center floor, sometimes very literally on the data center floor. And back then, I learned some core truths about networking that have been evergreen and are still true today. The first of those is that we always want networks to be as reliable, performant, and secure as possible. That's just as true today as it was then. And for my entire career, I've always been involved in a constant process of upgrading networks. It's never stopped. There's no point at which we are done. And at a deeper level, I also learned that the reason we want networks to be as reliable, fast, and secure as possible is we mostly don't want people to ever have to think about the network or networking. We want the collaboration and information sharing experiences that networking enables to seem like magic and to be taken for granted by ordinary users. And so also back then, when I was learning about networking, one of the first tools I encountered to understand how networking actually works under the hood is the OSI layer model. This great abstraction for all of the protocols and layers that have to interoperate to power the networking experiences that we're all used to. And it has high-level layers like the application layer for HTTP protocols for the web or SMTP protocols for email. And it has low layers all the way down to physical, things you can hold in your hand like copper and fiber optic cables. And in my time working on networking, I've seen us add more and more layers to this model. The first example of that is about 20 years ago when it became increasingly common for customers to encrypt their traffic with protocols such as TLS, SSL, and now QUIC these days, inserting a new kind of invisible transport encryption layer between traditional application and lower level networking protocols. But at AWS, under the hood, we actually have many more layers that we innovate on and we see to power the virtualized networking experiences that our customers get. If you were to look at actual traffic on the wire in the AWS network, you would see that under the layers that the customer controls, we have layers for doing transparent VPC encryption, for doing our software-defined network encapsulation. We add our own transport to network layers on the physical wire. And right down, as close to the bottom as we can possibly do it, we also have pervasive physical network link encryption. And you've probably noticed already that we have 3 different encryption layers in this diagram. And that's very, very typical these days and very common. If you were to look again at that traffic, it wouldn't be at all unusual that customer traffic is encrypted 3 or even more times over when it's passing around in the network. Those layers do provide defense in depth and additional protection. You know, if there was a security issue in one layer, the others can compensate. But they also provide slightly complementary forms of security in those encryption. And so because this is so pervasive and such a deep part of the network experience that our customers have these days, I wanted to do a bit of a deep dive into this. And let's start with the transport encryption layer. So that's the layer we're probably most familiar with. And at AWS, we maintain our own open source implementations of the TLS, SSL, and QUIC protocols. And we also maintain our own open source general purpose cryptography libraries. And our top priority with those implementations is security and safety. And we've made really deep investments, including mathematical modeling and formal verification, to ensure that those implementations are secure and safe and don't have common security issues that have plagued some implementations. But our second priority with these implementations is performance. We know that because this encryption is now so pervasive, and because essentially every customer demands that their traffic is always encrypted with at least one of these protocols, which are always supported by an AWS service too, We've also made investments in benchmarking suites that can instrument and look inside these implementations and help us build and find optimizations that can dramatically speed up the network experience. And I just want to take a quick look at one of those optimizations to give you a flavor of a typical example. Our network encryption engineers are going in and operating at the instruction set level and making optimizations both for Graviton and x86 that can deliver pretty dramatic performance improvements. This example I have is of a particular low-level cryptographic algorithm, modular inverse, and we were able to achieve about a 10x performance improvement, taking it from about 45,000 nanoseconds per operation to almost a tenth of that. And not just that it's about 10 times faster, it's also much more consistent in its performance, which is really important for both reliability and security. And with these kinds of optimizations and other simple optimizations, like moving from the RSA signature algorithm to the ECDSA signature algorithm, we're able to deliver real savings that help customers reduce the sizes of their fleets and give us collectively energy savings that help us meet our climate pledge goals. That's how large and dramatic some of these savings can be. If you were to look at a typical network-heavy customer workload, such as a web server, it's not at all uncommon. The majority of the CPU time that's being spent on that is on things like key agreement and encryption and decryption of traffic. So this work is super critical. Now, this transport encryption does a great job of hiding what's inside traffic. If someone were to tap a cable and just see this encrypted traffic, they really wouldn't have any idea what's going on inside that traffic. That's the point of encryption. But it doesn't do as great a job of anonymizing that traffic. It's still clear who the traffic is from and to if you're just using these kinds of protocols. It's also clear when and how much is being sent. And to help mitigate and provide extra defenses against that kind of threat, we also decided we wanted to have pervasive network encryption built in to our VPC system. And so in 2017, we built VPC encryption, where any traffic between any two Nitro EC2 instances is just encrypted by us by default. The customer doesn't have to do anything, doesn't have to turn anything on. It's all there, accelerated in hardware with incredibly fast performance. We also encrypt all traffic when VPCs are peered between regions. And in both of these cases, this provides an extra layer of anonymity. And this might sound a little simple. Take a super fast encryption chip, put it into the network packet pipeline, encrypt, decrypt the traffic, and so on, and you're done. But it's actually a significant challenge at our scale. The scale of the AWS network actually exceeds the original design limits of the AES encryption algorithm. If we were to simply encrypt traffic in the normal recommended best practice ways that AES is supposed to be used, we would hit its safety limits within seconds in some cases. So under the hood powering this encryption is a control plane and transactional secure systems that we've developed to ensure that the right keys are in the right places at the right times, ensuring that keys are on every receiver before any sender ever attempts to use it, and also that when keys are ready to be retired, that they're securely erased, and that nobody has access to keys for the entire life cycle in between. And in addition to this, we know we also have customers who have hybrid workloads, and all of their traffic isn't necessarily being generated inside the cloud. And we want to provide as much encryption as we possibly can everywhere. And so we also developed our lever network link encryption. And so the physical links that leave our physical control, so whether that's between two AWS data centers that are a few meters apart or hundreds of kilometers apart, are encrypted and protected by this low-level lever physical network link encryption, including the AWS backbone, which interconnects all of our AWS regions. When we first developed this, we built on top of some industry standard protocols, such as MACsec and optical link encryption, but we also did engineering so that for the first time, those protocols could operate with additional post-quantum security properties, just making sure that that encryption would be resilient to potential analysis by future quantum computers that may exist someday. These layers all interoperate to provide those slightly different security properties: pervasive transport encryption, anonymity, and post-quantum safety. And let's take a look now at where they're used in the network in the context of our global footprint. So in the last year, we have increased our network backbone capacity by 80% to keep up with customer demand. That's over 6 million kilometers of fiber optic cable, just a truly enormous scale. And it's not simply that we have that enormous amount of raw physical capacity in the network. We've also been increasing the densities and rates of information that can be transmitted over that network. When we first built the AWS backbone, we had standardized on a 10 gigabits per second standard. And over the years, we've upgraded it to first 25 gigabits per second, 100 gigabits per second, and now 400 gigabits per second is our common standard on this network. And at this kind of rate of information sending, it takes a phenomenal amount of engineering and physics to make things happen. If you do the math, to send data at 400 gigabits per second, the transceivers that are encoding this information as light in a cable have attoseconds, fractions of nanoseconds, to actually encode this data. Light itself can barely travel the length of one of these transceivers in that time. So you're really rubbing up against some core physical limits, which meant this encoding has had to happen in parallel, using different phases and multiple pulses at the same time so that those rates of information can be increased. And it's just staggering engineering, in my opinion. And this is what's powering the connectivity between our global infrastructure. The AWS backbone is what connects AWS regions to other AWS regions, and AWS regions to our local zones, and to our points of presence where we have direct connect and edge connectivity. And our network is our network is always configured to prefer the AWS backbone and only use the AWS backbone for connectivity between our locations. We don't send this traffic using third-party providers. So we're always able to ensure that we have things like that lever network encryption operating and protecting our customers' traffic. Now let's take a look at our regions and our region expansions. We think of our regions as collections of data centers and availability zones spread across a geographic area roughly the size of a metropolitan area. And we're constantly expanding the number of regions we have. Most recently, in August this year, we launched our Kuala Lumpur region. And we're not planning on stopping there. We've announced plans for 18 new availability zones and 6 regions, including in Mexico, New Zealand, the Kingdom of Saudi Arabia, Thailand, Taiwan, and one that I'm particularly excited about, which is our first AWS European Sovereign Cloud region in Brandenburg, Germany. And I don't see this ever stopping. This is always one of our most important missions, increasing the number of regions that we have. But we know that even with this breadth and density of regions that we have available, we have customers who still need compute locally in their cities where there may not be an AWS region yet. And so back in 2019, we launched local zones, where we have these pockets of AWS data centers that are in other cities connected back to a parent region. We now have 41 of these local zones, including 17 outside of the United States. And as a great example of the extended reach that these local zones can achieve, we have my personal favorite new local zone that I'm happy to volunteer and visit anytime, which is in Honolulu, Hawaii. I'll go anytime. And we have customers such as Athena Health who are using local zones to help modernize their applications. Athena Health had a legacy system using a multi-purpose database and faced issues with developer productivity and operational efficiency. And Athena Health used AWS local zones to run modern containerized applications with low latency access to that on-premises database within the same city. This hybrid approach helped them accelerate their modernization program and speed things up. And we have partners too, such as Palo Alto Networks, who also use AWS local zones in 5 continents to help deploy their Prisma Access Service endpoints and their Zero Trust access networks to protect data as close to users as possible. By deploying so broadly and using those local zones, Palo Alto Networks were able to achieve up to a 50% reduction in network latency for their customers while maintaining 5 nines of availability. That's staggering. And we've also long believed that customers should have as much control over their data as possible. And one of the most extreme cases for that is our government scale, public sector, and highly regulated customers, where sometimes they can have stringent data residency and data isolation requirements that go so far as to require even physically dedicated infrastructure. And so last year, we launched AWS Dedicated Local Zones, a fully managed AWS data center and local zones that's dedicated to a single customer and that customer's community in a location that they specify. And we have customers such as the Singapore Government Smart Nation and Digital Government Group who've been using dedicated local zones to meet their most stringent data isolation and security requirements, which helps them run some of their most sensitive workloads in the cloud securely. In addition to helping the Singaporean government achieve those cybersecurity requirements, dedicated local zones also gives its agencies a seamless and consistent cloud experience. They're able to use the services and APIs that they're used to. My new favorite example of that is that we've just recently added support for Amazon S3 running autonomously inside those dedicated local zones. I never imagined that we'd be able to take a hyperscale service such as S3 and build a copy scaled all the way down that it could run dedicated for a single customer in a deployment such as a dedicated local zone. I'm still staggered by it. Now, these private and hyper-local compute solutions are used by customers with those data isolation and latency targets, but almost all of our customers have some kind of need for private connectivity into the cloud. And that's where Direct Connect comes in. And in the last year, we've expanded Direct Connect to now over 140 locations globally. And this enables faster than ever connectivity for lower and lower latency experiences. And we've also rolled out that 400 gigabits per second standard to our Direct Connect locations so that there are no bottlenecks and there's increasing amounts of capacity to serve our customers' needs. We have customers such as Riot Games, with hundreds of millions of global players across some of the world's most popular PC games, such as League of Legends, using Direct Connect and other services, including local zones, to get connectivity using the shortest paths across the AWS backbone. This lets them achieve ultra-low latency and give them experiences where their gaming customers can't perceive any kind of delay. Now, we also know that the network isn't always the right answer for getting data into the cloud. And we've long had services where a customer could take their data on their media, like SSDs, and send it to us, and we would import it into the cloud for them. But we've now also launched Data Transfer Terminal, which makes this more convenient than ever. This is locations in your city that you can bring the media to, and will be imported there and then. And you keep control and supervision of those media, and it also helps eliminate risks like what if the media were lost in transport? What if a courier had an issue? Which can help reduce the amount of spare media that you need to keep around for all that extra time that things are in transit. And so customers such as Rivian have been able to use this to achieve speed-ups of up to 3 times faster for some of their training workloads. This has speeded up their autonomy feature roadmap and given them faster time to value. And also, as they do this, they're able to maintain control of those media. Now, these solutions are around private connectivity. But we've also been making massive expansions on our public internet connectivity side too. So when I joined AWS, I joined to help build CloudFront. My first day was writing code that helped CloudFront operate. And we were super, super excited what we were building. And I remember being blown away that we were going to launch with 14 points of presence. At that time, that was a competitive number, and it was a demonstration of global reach. Well, now we're at over 700 public internet points of presence. We're closer than ever to all of those end users spread across the world, giving ultra-low latency experiences. And in addition to that, we also now have over 900 CloudFront embedded points of presence. So these are CloudFront POPs that are embedded in ISP and mobile operator networks to serve directly those end users. And that's being driven by the super popular use cases and demand that customers are placing on top of CloudFront. And one example is F1 TV. So F1 TV is the official streaming service for Formula One and allows users to watch live races, behind-the-scenes content, replays, and more. But Formula One is unlike any other sport in that a huge number of users, millions, join to stream an F1 race in just the first 3 minutes of that race, creating an incredibly aggressive scaling demand. But F1 TV is able to use CloudFront to meet this intense scale and capacity requirement, scaling to millions of concurrent streams and authentications in real time, giving a high quality experience. We also have gaming customers such as Supercell, the Finnish game developer who are behind games such as Clash of Clans. And they've been able to reach over 250 million distributed players using services such as CloudFront, local zones, and global accelerator under the hood. And they've been able to use this to achieve single-digit millisecond latency experiences, staggeringly low and incredibly close to those end users. It's incredible. Now, all of this capacity in our global footprint and global networks would be for nothing if we weren't able to match that power in the AWS data center. And so long ago, we realized that we would have to give customers dedicated hardware-accelerated network experiences as part of EC2, which is why we built, or one of the big reasons why we built the AWS Nitro platform, where we do our network acceleration, network virtualization, and network encryption in dedicated chips that don't have to steal resources or consume anything from the customer's own instance. And ever since we've built Nitro, we've been constantly racing and ratcheting up the amount of bandwidth and capacity that it can sustain. And that's a never-ending race. And it's gone leaps and bounds, exponential increases are what we're used to. Many of these increases are driven by software optimizations and improvements we're able to make, but a lot are also driven by the fundamental hardware and getting those next iterations. With our most recent Nitro V5 chip, we're able to sustain 200 gigabits per second from a single chip. But now, with the introduction of Nitro V6 hardware, we're actually going to be able to sustain 400 gigabits per second, doubling that right away on our Nitro V6 instance types. And with that, in combination with putting multiple Nitro chips and multiple Nitro cards inside a single instance, we're able to just constantly increase the ceiling on how much bandwidth a customer can generate. And the numbers are staggering. Today, our record is about 3,200 gigabits per second from a single instance. When I was first building nation-scale backbones, we were barely at 1 gigabit for a whole country. And this is 3 times that from a single instance type. But now, with the introduction of Ultra Server for AI and machine learning training workloads, we're really blowing away the ceiling on that. So we're now going to be delivering 12.8 terabits per second from a single Ultra Server. That is more bandwidth than many countries use today for their entire population's internet access from a single instance. And that bandwidth ensures that those instances can collaborate in all of that real-time machine learning, sending back and forth all of the training data and weights and improvements and so on. And we're not just focused on bandwidth. We're also focused on latency and reducing the amount of time it takes to get a packet from A to B, because we know that has a disproportionate impact on the customer experience too. With our latest generation of the P5 instance type, the P5 EN instance type, we've been able to deliver a 35% improvement on the latency compared to previous generations. And this isn't just a micro benchmark or something that, it's just a number. It reflects in speed-ups for the real-world workloads. And we're able to see up to 55% improvements on those overall workloads just because of that latency change. That's how critical latency is to these applications. When you've got thousands of machines waiting on potentially other thousands of machines, latency can start to add up really, really quickly. So we know to focus on this. Another dramatic example of where latency really matters is just what humans can perceive. So I live in Seattle, Washington, but I collaborate and work a lot with my colleagues in the EC2 office in Cape Town, South Africa, where EC2 was first developed. And if you were to pick two cities on Earth, they're about as far apart as possible. It's hard to do any further than those two cities. They're almost perfect antipodes. And when I'm on a phone call or a video call with my colleagues, I can perceive that latency. It is noticeable. It is actually something a human can perceive. And those machine learning and high performance computing workloads are doing that even inside the data center. Those things operate at such fast critical speeds that latency becomes so perceptible to them. And we want to eliminate every possible source of latency in our network that we can find that's possible. And so one innovation that we've been working on for years and that I'm really excited to talk about today is that we have been introducing and have hollow core fiber in our network directly. And the reason that's so important is that if you remember anything from science class or physics at school, it might be that the speed of light is the fastest speed anything can go in the universe. It's to do with relativity and things I've forgotten about. But we don't even typically send information at that speed of light. Normally when we're sending information, it's being sent through glass. That's the medium the fiber optic cables are made of. And the speed of light in glass is only about 2/3 the speed of light in free air or the vacuum of space because of the refractive index. And so we've been working with foundational science, material scientists, fabrication and manufacturing experts to be able to produce lengths and strands of fiber that aren't fully made of glass, that have a hollow core. And by sending the information through that hollow core, we're able to achieve the true speed of light, the one you would see in a physics textbook. And this takes enormous amounts of engineering beyond even that manufacturing. This is the casing, the step-down casing for a hollow core fiber. It's made of pretty rigid glass to protect that hollow core because the hollow core fiber itself is just a little more brittle than typical fiber is for obvious reasons. And that presents real physical engineering challenges that we have to solve inside data centers. And it's been a lot of work, and it's great to see the payoffs and to see real workloads that are being sped up because we're able to do something as dramatic as now sending the information through that hollow core. Now, it's no good to have ultra low latency if when you send the packets, they're just going to run into congestion and bottlenecks upstream anyway. And so that's the reason why we've always and also developed elastic fabric adapter. And what EFA is a technology we developed specifically for AI and ML training workloads, HPC workloads, and other workloads where large collections of machines have to talk to one another and talk to other things. Internally, the AWS network is made up of many, many links. And there are literally millions upon millions of paths that traffic can take at any given time. EFA is aware of this topology. And what it's doing is taking the information the customers want to send, and it's splitting it up and dividing it and sending it in parallel paths across this network. And it's also aware of where congestion may occur, or could be occurring, and can react to that in real time and ensure that the paths that are being taken are the ones that are the most optimal. And this is what allows us to scale up and power networks that are larger than ever. If we take an instance type like that Ultra server that has 12 terabits of connectivity, we're able to scale up even well beyond that using EFA. We're able to connect thousands and thousands of those machines in large-scale clusters and fabrics. It's phenomenal, and EFA's been able to work in harmony with technologies such as Trainium2 to ensure that the network isn't going to be a bottleneck in the way of all of that training compute. It's absolutely staggering. And we know too that customers don't just need their instances to talk to one another for that training. They also need to be able to get training data in, RAG data in, fine-tuning data in, to be able to store snapshots when needed. And so we've also added native EFA support to storage services. So we now support directly EFA connectivity to Amazon FSx for Lustre. So that those same optimizations can be used when you're retrieving or storing data. We also know that when you've got thousands of instances and you really want to use EFA for all your connectivity, it can be a nuisance to have traditional network interfaces with IP addresses and having to assign every box a unique IP address and think about all of that. So we're also excited that we now support EFA-only machine learning instances. So it can have just EFA connectivity and really simplify the amount of network configuration that customers need to set up. So far, I've been talking about what we've built for you under the hood, but I'd also love to talk a bit more about what you can use to build on top of AWS. And let's start with VPC, the Amazon Virtual Private Cloud. I think one of the core features of Amazon VPC has always been security groups. A simple technology that lets customers categorize instances and interfaces and so on into collections of like things. And customers love the simplicity of security groups. They are easier to use than other approaches that predate them, like access control lists. But traditionally, it has only really worked for the instances and network interfaces themselves. Well, we're trying to make it simpler than ever. And we've now have native support for security groups directly in AWS Transit Gateway and Network Load Balancer. So the customers can use security groups, thank you, can use security groups to directly control security and permissions inside those products, greatly simplifying. And we know too, the customers want to be able to reuse security groups. And we now have shared security groups so that you can define a security group once and reference it in more than one VPC and across even AWS accounts. It's staggering. And as simple as security groups make it, we have heard from customers whose primary need is they just have a network or some instances that are doing some sensitive data processing, and their number one rule that they want to enforce is that it can never end up having public connectivity, whether that's through an internet gateway or a NAT gateway or through any other means. And so we've now also launched VPC block public access, where customers can have an extra bulletproof declarative control that says, no matter what else, I want to ensure that this VPC or this subnet has no means to access the internet, that it can't simply be overridden or enabled. And these extra controls give a really deep peace of mind and additional security. Now, to talk more about what customers can build on top of our services, I'd like to invite a customer on stage. And so I'd like to please welcome Ragini Lalwani from Goldman Sachs. Thank you.
Thank you, Kam. Hi, everyone. I'm Ragini Lalwani, and I'm a managing director at Goldman Sachs. I'm responsible for the cloud dev platforms, which also includes cloud connectivity. Now, I've been with the firm for almost 17 years, and in my time there, I've had a first-hand view into the evolution from bare metal to virtualization, and now to public cloud. Most of you associate Goldman with financial services. And while that is true, I'm here to also tell you that we are underpinned by a robust group of over 12,000 engineers. These engineers work tirelessly to make sure that the machinery behind the scenes works securely and successfully for our customers. Now, with respect to our cloud journey, I want to talk to you about the 3 pillars that influence all technology decisions at Goldman. These are compliance, security, and scalability. Consequently, we follow very strict guidelines to ensure that when we are building and implementing applications, we are taking these factors into account to handle any sensitive information. This is why when we wanted to start our cloud journey, we partnered closely with AWS to help shape and supplement individual services to suit the financial services landscape. For example, we worked very closely with the KMS team to help build and design the Bring Your Own Key KMS CMK feature and all of its corresponding controls. We also collaborated with them on an import feature that supported our ability to securely scale sensitive workloads. These workloads traditionally ran on-premise, and now we were able to enhance data protection and integrity using KMS. As a result of this now, KMS is a key component to our data protection strategy at Goldman Sachs for any services deployed on AWS. Now, we also collaborated with AWS and advocated for certain foundational services like CloudTrail and KMS CMK to be embedded and enabled with every new service launch from the outset. These capabilities supported us to launch and successfully build our grid on AWS back in 2016. I want to spend a little bit time now talking about our zero trust approach and our network architecture. It became clear to us pretty quickly that a zero trust approach and building secure, isolated boundaries was going to be paramount for our success in the cloud. Our key security tenets for this are around strong authentication and authorization, clear network segregation, and well-defined access controls. Initially, when we began our private-only VPC situation, we had access to it for our respective teams via Direct Connect. We further strengthened this with built-in IAM controls, and that was how we started. But over time, as we grew and understood the potential of the cloud for our use cases, our network stack naturally grew as well. Then we had VPCs across more regions and more accounts. Over the last 5 years, the number of accounts that we have grown over 10 times, and the number of VPC endpoints have grown by 20 times. That's amazing growth in the last 5 years itself. This growth has happened on top of many services like transit gateways, direct connect gateways, application and network load balancers, et cetera. A specific service that supported us quite a bit operationally was Cloud WAN. Now, we have been expanding at a rapid pace and reducing the time it takes to onboard a new region or a new service is paramount for our customers. We want to enable teams without compromising on security or their need for isolation. That's where Cloud WAN has helped us. It simplifies our connectivity strategy and accelerates our support for additional regions. Prior to Cloud WAN, enabling multi-region and conditional routing involved a lot of steps. We needed static route configurations. We needed to associate tables with transit gateways, followed by peering between them. This process was error-prone and caused challenges for us. We had to do extensive troubleshooting, and we had to debug quite a bit. Suffice it to say that overall, onboarding a new region for a large platform was slow. Cloud WAN has changed that for us and become the one-stop solution for effective routing within AWS. And it helps facilitate our multi-region connectivity across VPCs, which are in different regions, which are in different accounts, et cetera. Cloud WAN segment routing also supports us when routing traffic across the network to security control points. It has a simple policy statement setup, which allows us to bring our entire growing global network and the entire policy definition in one location. This simplifies things from a management plane perspective and is a huge win for us. Now we are able to bring up a region in less than a week. I now want to spend some time talking about our zero trust approach and specifically about how we use an account as a strong isolation boundary. This provides us with the access control that we need, but it also provides us with limiting the blast radius. This may occur because of potential misconfigurations, et cetera. Now, we have been very, very deliberate in our use of the multi-account strategy. And we've talked about it in several sessions here at re:Invent as well. You can look up breakout sessions in 2018 and 2020. Now, to build on the benefits that we want for this account segmentation, we used AWS Private Link. This private link setup was allowed in areas where appropriate from our side for cross-account access and cross-VPC access to some of our systems. Now, private link, in terms of its setup, supports service providers to expose their services as endpoint services. And on the other side, we're allow listing specifically accounts and IAM identities that create interface endpoints to connect to these services. This approach ensures a fairly granular access, and that's what we're after. These endpoint service definitions only allow access to resources that are behind NLBs. So that makes it even more scoped from an access perspective. Further, we're also making sure that this connectivity only happens one way from the service consumer to the service provider. So it's specifically very point-to-point. Now, we've talked about how we did this private link setup. I want to talk to you about where we use the private link setup. The most common use case, which I'm sure all of you are doing, is connecting to AWS native services. But we also use it to connect to other Goldman Sachs services, whether they're hosted on AWS, whether they're hosted on-premise, whether they're hosted on another cloud provider. Another place where we use it is connecting to third-party SaaS services like Snowflake, MongoDB, Datadog, et cetera. But the most interesting place where we're using it is for acquisitions. In today's day and age, when you do an acquisition, most likely they are also running on the cloud. And now we're able to use Private Link to smooth out the integration process until that acquisition is fully technology integrated into our firm. So in conclusion, we have used a bunch of networking services to grow our cloud footprint and help in our migration. We're now looking forward to exploring the value of VPC lattice. We're looking at its service-to-service connectivity model and seeing what it can bring to our firm. There are a few specific features that we are digging deeper into that are very interesting to us. The first one is fine-grained authorization for IAM. The second one is reducing the dependency on IP addressing, or ENIs, with local link access, link local access. And the third one is native integration with AWS compute resources and service network management. Overall, we're looking at Private Link and VPC Lattice to be the areas that we want to explore. Before I hand back over to Com, I want to thank the unsung heroes behind this segment, Mike Ahern, who's here from Goldman Sachs, along with Kai Huang and Sujoy Saha, who couldn't join us today, and Harsha Sharma, Peter Seremides, and Anup Devani and Rick Armstrong from AWS. With that, over to you, Com.
Thank you very much. So as you heard firsthand there, we have two different approaches to networking that we often see with different customers, teams, and workloads at AWS. We have teams and workloads who like to treat the cloud and model it as they would a traditional enterprise network, using familiar concepts, IP addresses, routes, and so on. And we have customers and teams and workloads who don't want to think about any of that, who prefer to abstract all that away and use our serverless offerings and other ways of using networking that don't make you think about those things so much. We never see either of those models as better or worse than the other. We fully support them both. And not just that, but we increasingly have more and more features that are about helping customers live in both of those worlds at the same time, because we're seeing that be more and more common. The best example of that, as we just heard, is Amazon Lattice, where customers can have a completely managed serverless service mesh that integrates into their container environments and so on, but also bridges into traditional networking experiences and lets them connect with things on premises, elsewhere, and so on, together with all of the observability and so on that they would expect. And we've been adding more features to make this easier than ever. We now have TLS pass-through support on Lattice so that you can use your existing backends and maintain your TLS and SSL settings and connectivity there. We've got built-in ECS support so that it can be enabled for ECS deployments more easily. We've native support for TCP resources so that things such as databases and cache clusters can be referenced. We've simplified on-premises access. And this theme continues across our other offerings. We've added UDP support to AWS Private Link and Network Load Balancer. So now it's possible to use NLBs and Private Link for services such as voice over IP or virtual desktops and other UDP-based protocols. We also know that customers sometimes have a service in one region but want easier private connectivity for that service from another region. We've also added cross-region support to AWS Private Link, so the customers and partners and independent software vendors can now offer private link services in any region where the actual backends for that service live in another region. This was built with support for data sovereignty controls to ensure the customer's data sovereignty requirements are still respected. And it's got an extensive portfolio of third-party providers who are integrating with this. And we've also removed the need to have a network load balancer in the path when using Private Link. It's now possible to connect directly to some resources such as databases and cache clusters. And I'm really thrilled that we're not doing all of this alone. We have an amazing set of partners who are supporting these features, including Grafana Labs, Palo Alto Networks, Redis, and more. Now, we've talked about all of the global capacity expansions and features we've been adding to our systems. But I also want to talk about how customers can handle challenges and bad days in the cloud. And what I mean by bad days is things like security events if a customer is the victim or target of things like a security threat. And we like to be really proactive about those things and to ensure that customers always have the strongest security posture that can be enforced. And so recently, we've been more public about some of the work we do behind the scenes on threat detection and threat analysis, and the work that we're doing to constantly look for and detect threats that are out there. We recently talked about MadPot, our system for doing real-time threat analysis and threat detections, which every day is analyzing 100 million interactions and flagging as suspicious up to 500,000 or so events. And these feed into our threat protection systems. We're also analyzing DNS data and looking for potentially suspicious DNS queries. If a customer's infrastructure is compromised, it's not uncommon that an attacker might do something like attempt to connect to a command and control network, or maybe attempt cryptocurrency mining to just get something out of those resources. These are signals that show up in DNS data. So we've been taking all of this work that we do for advanced threat analysis and building it into our security products. And we now have support in Amazon Route 53 Resolver DNS firewall for blocking advanced DNS threats based on these systems. We've also made it easier than ever to trace the activity that's happening on your network. And so with our zero trust offerings, we're making it easier than ever for customers to be able to correlate activity in the network at the level of a particular flow or connection event and trace that back to who generated that or what system generated that. Traditionally, this has required taking many different log sources, correlating events, and it could take an engineer a lot of time to answer a question like that. But with these zero trust offerings, they're able to answer those questions in seconds, which makes a really big difference to things like threat response, like identifying which user may have had their account compromised super quickly can make a real practical difference to how those events are handled. And Amazon Verified Access, our zero trust product, also has added support for resources, and so can connect directly to TCP services, such as databases, with super granular policies that still give you all of the control you need. And on the observability side, we've seen that as customers build larger and larger systems on top of AWS, and also as they operate in hybrid modes where they're using on-premises and AWS, it can become challenging to determine where is the source of a potential network issue. And on the AWS side, we do an unbelievable amount of pervasive monitoring of the AWS network. There are constantly running probes that are being sent across every link. There are also passive measurement systems that are doing things like looking at light signal levels and predictive failure analysis to ensure that the availability and reliability of the AWS network is absolutely best in class. But we know that even with that, links can sometimes still spontaneously fail. If a link is out there in the real world on streets, then a construction event might break a link, and something has to route around that. We also know that customers' own configurations can be a source of networking issues. I was working with a customer recently diagnosing a networking issue, and the root cause turned out to be simply had too many containers on one instance, and it couldn't handle the amount of networking that was being processed there. And so I'm really happy that we've now introduced Amazon CloudWatch Network Monitoring, which is a system where we're generating real active traffic and flows with an open source agent that the customer can run on their instances and elsewhere and get real-time visibility of what's actually happening with traffic. This is sending traffic across many paths similar to that EFA technology and collecting that back and turning it into a real-time view. And this view also integrates with other third parties and partners such as Cisco, so that customers can have a consistent view across both their cloud infrastructure and their on-premises infrastructure. This is one of my favorite features that we've launched. I have other favorites too. In fact, we've launched a lot of features in the weeks leading up to reInvent, way more than we could cover in today's session. But before we ended, I did want to pick out some favorites, and 3 in particular. I think a feature I've seen many customers ask for, and we now have, is Amazon CloudFront supporting directly VPC origins. This means you can now have a dynamic origin for CloudFront running on EC2 instances that with private connectivity. There's no need for that instance to be exposed to the public internet. Another favorite feature of mine is that Amazon API Gateway now supports custom domain names for private APIs. So you're able to create a private API and give it a name that you choose and is easy to remember, which is just very nice and convenient. And then if you're a customer who deals with, say, large-scale streaming events or other types of workload that have large spikes that can't be forecast, They just happen, but you know the time they're going to occur. Then we now have support for LCU reservations. You can pre-provision your load balancers so that you know you'll be able to handle that event on the day that it occurs. With these features and more, we're making it easier than ever for customers to have a seamless, reliable networking experience on top of AWS. Thank you so much. I'm so excited about everything we've shipped on networking, but nothing excites me personally more than seeing what customers build on top of our systems to deliver to their end users and systems and their customers. And so over the next year, I'll be really keen to see what customers are able to build on top of these offerings and products. Thank you very much for coming. Everybody have a really great replay and have a great rest of reInvent.